Hello and welcome to Earth Science Lecture 5, Sedimentary Rock. Weathering goes on all around us, but it seems like such a slow and subtle process that it is easy to underestimate its importance. Yet, it is worth remembering that weathering is a basic part of the rock cycle, and thus is a key process in Earth's systems. Weathering is also important to humans, even to those of us who are not studying geology. For example, many of the life-sustaining minerals and elements found in soil, and ultimately in the food we eat, were freed from rock that was weathered. So, all materials are therefore susceptible to weathering. Consider, for example, the fabricated product concrete, which closely resembles the sedimentary rock called conglomerate, which we'll see soon. A newly poured concrete sidewalk has a smooth, unweathered look. However, not many years later, the same sidewalk will appear chipped, cracked, and rough with pebbles exposed at the surface. If a tree is nearby, its roots may grow under the concrete, having a buckling effect. These same natural processes that eventually break apart a concrete sidewalk are also able to act to disintegrate rocks, regardless of their type or strength. Weathering occurs when rock is mechanically fragmented or disintegrated, or chemically altered or decomposed. Mechanical weathering is accomplished by physical forces that break the rock into smaller and smaller pieces, without changing the rock's mineral composition. Chemical weathering, on the other hand, involves a chemical transformation of the rock into one or more new compounds. In nature, 4 important physical processes lead to the fragmentation of rock: frost wedging, salt crystal growth, expansion resulting from unloading, which is called sheeting, and biological activity. In addition, although the work of erosional agents such as waves, wind, glacial ice, and running water is usually considered separately from mechanical weathering, it is nevertheless related. All of these mobile agents move rock debris, particles, and will continue to be broken and abraded. And so we're going to take a look at each of these 4 types of weathering processes. So let's go ahead and start with frost wedging. When liquid water freezes, it will expand by about 9% in volume. If water works its way into the cracks of rocks, well, the freezing water will then enlarge the cracks, and the fragments will eventually break off. This is the concept behind frost wedging, the mechanical breakup of rock caused by the expansion of freezing water in cracks and crevices. And there's a nice graphic on the right-hand side that aids this discussion. If you leave a glass bottle of water in the freezer a bit too long, the bottle will break. The bottle breaks because the liquid water has the unique property of expanding by that 9% upon freezing. This is also the reason that poorly insulated or exposed water pipes rupture during frigid weather. Research has shown that frost wedging can also occur in a different way. It has long been known that when most soils freeze, they expand due to growth of ice crystals. These masses of ice grow larger because they are supplied with water migration from unfrozen areas. As more water accumulates and freezes, the soil is heaved upward. A similar process occurs within the cracks and pores of spaces in rocks. These lenses of ice grow larger as they attract liquid water from surrounding pores. So the growth of these ice masses gradually weakens the rock and causes it to fracture. The second type of weathering we talked about, or at least introduced, was salt crystal growth. So another expansive force that can split rock is created by the growth of salt crystals instead of ice. Rocky shorelines and arid regions are common settings for this process. It begins when sea spray or salty groundwater penetrates crevices and pores in rocks. As this water evaporates, salt crystals form. As these crystals gradually grow larger, they weaken the rock by pushing apart the surrounding grains or enlarging tiny cracks. This process also contributes to the crumbling of roadways where salt is spread to melt snow and ice in the winter. The salt dissolves in water and seeps into the cracks that's quite likely originated from frost action. When the water evaporates, the growth of the salt crystals further breaks the pavement apart. And here's a nice image showing this. You can actually see where salt crystals grew in the past. The third type of weathering we will introduce is sheeting. When large masses of igneous rock, particularly those composed of granite, are exposed by erosion, concentric slabs begin to break loose. The process generates these onion-like layers called sheeting. It takes place due to the great reduction in pressure that occurs when overlying rock is eroded away in a process called unloading. As the overburdened material is removed, the outer parts of the granitic mass expand more than the rock below and separate from the rock body. Continued weathering eventually causes the slabs to separate and peel off, creating domes. Excellent examples of these exfoliated domes include Stone Mountain in Georgia and Half Dome in Yosemite National Park. Human activity can also play a role in the sheet-like fracturing as a result of unloading. In deep mines, large slabs of rock have been known to explode off the walls of newly cut tunnels. In quarries, fractures can occur parallel to the floor when large blocks of rock are removed. Fractures can also be caused by contraction as igneous material cools, or they can be produced by tectonic forces during mountain building. Fractures produced by these activities often form a definite pattern and are called joints. Joints allow water to penetrate deeply and initiate weathering long before the rock is exposed. But more on that later. The main point here is when you have a deep body of rock and that becomes exposed for some reason, there's not a lot of weight pushing down on it anymore, so it gets pushed up, it's uplifted. And as it does so, it starts to crack and little sheets or slabs begin to fall off due to erosion and the loss of pressure. The fourth type of weathering was biological activity. The activities of organisms, including plants, burrowing animals, and humans, can cause weathering. Plant roots in search of minerals and water grow into fractures, and as the roots grow, they wedge the rock apart. Burrowing animals further break down the rock by moving fresh material to the surface, where physical and chemical processes can more effectively attack it. Where rock has been blasted in search of minerals or for construction projects, the impact of humans is particularly noticeable. Organisms play many roles in chemical weathering. For example, plant roots, fungi, lichens, and the such can occupy fractures or that may encrust a rock, produce acids that promote decomposition. Decaying organisms also produce acids. Moreover, some bacteria are capable of chemically breaking down minerals and harvesting the resulting energy, in essentially the same way that we obtain energy by breaking down the molecules of our food. Such bacteria can live at depths as great as a few kilometers. One of the last types of weathering we'll look at is the chemical weathering. So chemical weathering contributes to mechanical weathering. It does so by weakening the outer portions of some rock, which in turn makes them more susceptible to being broken by mechanical weathering. Chemical weathering involves the complex processes that alter their internal structures of minerals by removing and/or adding chemical elements. During this transformation, the original rock decomposes into substances that are stable in the surface environment. Consequently, the products of chemical weathering will remain essentially unchanged as long as they remain in an environment similar to the one in which they formed. Water is by far the most important agent of chemical weathering. Although pure water is non-reactive, a small amount of dissolved material is generally all that is needed to activate it. Oxygen dissolves in water and will oxidize some materials. For example, when iron is buried in moist soil, it will develop a coating of rust, iron oxide. So carbon dioxide can also dissolve in water to form carbonic acid. Rain acquires some of this dissolved carbon dioxide as it falls to the atmosphere, and such acids like this are readily decomposing many materials. Weathering begins the process of sedimentary rock formation. Gravity and erosional agents remove the products of weathering and carry them into a new location where they can be deposited. Usually, the particles are broken down further during this transport phase. Following their deposition, the sediment may become lithified or turned into rock. As piles of sediment accumulate, the materials near the bottom are compacted by the weight of the overlying layers. Over long periods of time, these sediments are cemented together by mineral matter deposited from water into the spaces between the particles. This forms solid sedimentary rock. The word sedimentary indicates the nature of these rocks, for it is derived from the Latin word sedimentarum, which means settling, a reference to a solid material settling out of a fluid. Weathered debris is constantly being swept from bedrock and is carried away by running water, waves, glacier ice, and wind. Eventually, the material is deposited in lakes, river valleys, seas, and countless other places. The particles in a desert sand dune, the mud on a floor in a swamp, the gravels in a stream bed, and even household dust are all examples of sediment produced by this never-ending process. About 75% of all rock outcrops on the continents are sedimentary. Therefore, we can think of sedimentary rocks as being composed of a relatively thin and somewhat discontinuous layer in the uppermost portion of the Earth's crust. This makes sense because sediments accumulate at the surface, so of course we find sedimentary rocks at the surface. It is from sedimentary rocks that geologists reconstruct many details of Earth's history. Because sediments are deposited in a variety of different settings at the surface, the rock layers that they eventually form hold many clues to the past and surface environments. Many sedimentary rocks are important economically, too. Bituminous coal, which is burned to provide a significant portion of U.S. electrical energy, is classified as a sedimentary rock. Other major energy resources, such as petroleum and natural gas, occur in pores within sedimentary rocks. Other sedimentary rocks are major sources of iron, aluminum, magnesium, and fertilizer, plus numerous materials essential to the construction industry. So I mentioned the term lithification previously, but we didn't go into it too much. Lithification refers to the processes by which sediments are transformed into their sedimentary solid rock. One of the most common processes of lithification is what is known as compaction. As sediments accumulate through time, the weight of the overlying material compresses the deeper sediments. As the grains are pressed closer and closer together, pore spaces are greatly reduced. For example, when clays are buried beneath several thousand meters of material, the volume of the clay may be reduced by as much as 40%. Compaction is most effective in converting very fine-grained sediments, such as clay-sized particles, into sedimentary rock. But lithification can occur in a second way. Because sand and coarse-grained sediments, such as gravel, are not easily compressed, they are generally transformed into sedimentary rocks by the process of cementation. The cementing materials are carried in a solution by water that percolates through the pore spaces between particles. Over time, the cement precipitates onto the sediment grains, fills the open spaces, and acts like a glue, joining the particles together. The minerals calcite, silica, and iron oxide are the most common cements. The cementing material is relatively easy to identify. Calcite cements effervesce, meaning they fizz when in contact with hydrochloric acid. Silica is the hardest cement and thus produces the hardest sedimentary rocks. An orange or red color in sedimentary rock usually means iron oxide is present. Materials that accumulate as sediments have two principal sources. First, sediments may originate as solid particles from weathered rocks, such as the igneous rocks described earlier. These particles are called detritus, and the sedimentary rocks they form are called detrital sedimentary rocks. Through a wide variety of minerals and rock fragments, we can find in these detrital rocks, clay minerals and quartz dominate them. Clay minerals are the most abundant product of the chemical weathering of silicate minerals, especially the feldspars. Quartz, on the other hand, is abundant because it is extremely durable and very resistant to chemical weathering. Thus, when igneous rocks such as granite are weathered, individual quartz grains are set free. So, Again, quartz dominates because it's just so strong, it's hard to break down. Clay dominates simply because it forms from the breakdown of the most common minerals that we find in Earth's crust, the feldspars. So again, here's another way to kind of classify some of our rocks. Here we're classifying them by the particle size. So let's go through each one a little bit. Particle size is the primary basis for distinguishing among detrital sedimentary rocks. When a rock consists of a significant amount of rounded gravel particles, the rock is called conglomerate, like you can see in the top top right. Gravel-sized particles can range in sizes from as large as boulders to the particles as small as peas. If the gravel-size particles are angular rather than rounded, the rock is called breccia. Angular fragments indicate that the particles were not transported very far from their source prior to being deposited, and so they have not been able to get rounded corners, and their rough edges are left behind. So this basically shows the breccia that we see in the bottom. This basically didn't travel very far, because if it did, it would have been eroded down, and so we wouldn't see sharp angles in these rocks like we do in the conglomerate. So this likely solidified more quickly or didn't travel as far. When sand-size grains rather than gravel-size grains prevail, the rock is called sandstone. When sandstone contains more than 25% of the mineral feldspar, we give it the name arkose. Shale, which is typically composed of clay minerals, is a name commonly applied to a very fine-grained sedimentary rock. However, in the strict use of the word, a rock can be classified as shale only if it exhibits the ability to split into thin layers. If a fine-grained rock breaks into chunks or blocks, the name given is mudstone. Siltstone, which is another fine-grained rock, is composed of slightly larger silt-sized grains intermixed with clay-sized sediments. Particle size also provides useful information about the environment in which the sediment was deposited. Currents of water or air sort the particles by size. The stronger the current, the larger the particle size carried. For example, gravels are moved by swiftly flowing rivers, rock slides, and glaciers. Less energy is required to transport sand, however. Thus, it is common to see it in wind-blown dunes, river deposits, and beaches. Because silts and clays settle very slowly, accumulations of these materials are generally associated with the quiet waters of a lake, lagoon, swamp, or marine environment. Chemical sedimentary rocks and biochemical sedimentary rocks are derived from materials or ions carried in solution to lakes and seas. This material does not remain dissolved in water indefinitely. Under certain conditions and due to physical processes, the dissolved matter precipitates to form chemical sediments. An example of chemical sediment resulting from physical processes is the salt left behind as a body of salt water evaporates. Precipitation may also occur indirectly through life processes of water-dwelling organisms that form materials called biochemical sediments. Many aquatic animals and plants extract the mineral matter dissolved in the water to form their shells and other hard parts. After the organisms die, their skeletons may accumulate on the floor of a lake or an ocean. So here we have another classification chart, this time based on their composition and their texture. And it again lists several different sedimentary rocks that we might find. So as we typically do, let's go ahead and step through several of these. Limestone, an abundant sedimentary rock, is composed chiefly of the mineral calcite. Nearly 90% of limestone is formed from biochemical sediments secreted by marine organisms, and the remaining amount consists of chemical sediments that's precipitated directly from the seawater. One easily identified biochemical limestone is coquina, a coarse rock composed of loosely cemented shells and fragments. So you can see that in the top right. Another less obvious but familiar example is chalk, a soft, porous rock made up almost entirely of the hard parts of microscopic organisms that are no longer the head of a pin. no larger, than the head of a pin. Among the most famous chalk deposits are the white chalk cliffs exposed along the southeast coast of England, as you can see in the bottom right. Inorganic limestone forms when chemical changes or high water temperatures cause calcite to precipitate. Travertine, the type of limestone that decorates caverns, is one example. Groundwater is the source of travertine that is deposited in caves. As water drops reach the air in a cavern, some of the carbon dioxide dissolved in the water escapes, causing calcium carbonate to precipitate. Dissolved silica, SiO2, precipitates to form a variety of microcrystalline rocks, that is, rocks consisting of very fine-grained quartz crystals. Sedimentary rocks composed of microcrystalline quartz include chert, flint, jasper, and petrified wood, as you can see in the images in the slide. So all of these contain microcrystalline quartz crystals. Very often, evaporation causes minerals to precipitate from water. Such minerals include halite, the chief component of rock salt, and gypsum, the main ingredient in rock gypsum. Both materials have significant commercial importance. Halite is familiar to everyone as the common salt used in cooking and seasoning foods. Of course, it has many other uses and has been considered important enough that people have sought, traded, and fought over it for much of human history. Gypsum is the basic ingredient in plaster of Paris. This material is used most extensively in the construction industry for drywall and plaster. In the geologic past, many areas that are now dry land were covered by shallow arms of the sea that had only narrow connections to the open ocean. Under these conditions, water continually moved into the bay to replace water lost by evaporation. But eventually, the waters of the bay became saturated and the salt deposition began. Today, these arms of the sea are gone, and so the remaining deposition is called evaporite deposits. Evaporite deposits are also found in enclosed basins on land. One example is Death Valley, California, where following periods of rainfall or snowmelt in the surrounding mountains, streams carry mineral-rich water into the lowest parts of the valley. As the water in those desert basins evaporates, materials that were dissolved in the water are left behind, forming a white, salt-rich crust on the ground that grows in thickness to generate a salt flat, as you can see in the image. In contrast to sedimentary rocks that are calcite or silica rich, coal consists mostly of organic matter. Coal is the end product of the burial of large amounts of plant material over extended periods of time. Because coal is produced by biochemical activity and contains organic matter, it is often classified as a biochemical or organic rock. Examining a piece of lignite, also called brown coal, under a magnifying glass reveals plant structures such as leaves, bark, and wood that have been chemically altered but remain identifiable. The initial stage of coal formation is the accumulation of large quantities of plant remains. However, special conditions are required for such accumulations because dead plants normally decompose when they're exposed to the atmosphere. Ideal environments that allow plant matter to accumulate are swamps. Stagnant swamp water is oxygen deficient, which makes it impossible for plant material to completely decay. At various times during Earth's history, such environments have become common. Coal forms in a series of stages, with each successive stage at higher temperatures and pressures drive off impurities and volatiles. Lignite and bituminous coals are sedimentary rocks, but anthracite is a metamorphic rock. Anthracite forms when sedimentary layers are subjected to folding and deformation associated with mountain building. Sedimentary rocks are particularly important in the study of Earth's history. These rocks form at Earth's surface, and as layer upon layer of sediment accumulates, each layer records the nature of the environment at that time. These layers, or strata, also called beds, are the single most characteristic feature of sedimentary rocks. Bed thickness ranges from microscopically thin to tens of meters thick. Separating the strata are bedding planes, flat surfaces along which rock tends to separate or break. Generally, each bedding plane marks the end of one episode of sedimentation and begins that of another. Fossils, which are the traces or remains of prehistoric life, are perhaps the most important inclusion found in some sedimentary rocks. Knowing the nature of life forms that existed at a particular time may help answer many questions about the environment. Fossils are important time indicators and play a key role in matching up rocks from different places that are the same age. Okay, so that's about it for sedimentary rocks. So as we typically do, let's finish up with some questions. So make sure you pause the video on each question and return when you think you have an answer so we can discuss. Number 1. Detrital sedimentary rocks are those that form blank. Okay, well, these are the rocks that form from an accumulation of material that is transported as solid particles. Detrital sedimentary rocks form from particles derived from mechanical and chemical weathering. Next, how are detrital sedimentary rocks classified? Okay, so the answer here is D, based on particle sizes. So detrital sedimentary rocks are classified according to their particle size, and you can see that in that classification chart we had previously. Here's a good question. What percentage of Earth's land area is covered by sedimentary and sedimentary rocks? Sediments and sedimentary rock. Well, again, it's very common on the surface, so in this case it's 75%. While most of the Earth's solid portion consists of igneous and metamorphic rock, most of the surface contains sediments or sedimentary rock. Number 4. The main mineral component of limestone is what? Okay. Limestone is composed chiefly of calcite. It is its most common mineral. And last but not least, what is the single most characteristic feature of sedimentary rock? Hopefully you remember this one. It's the last slide we looked at. It's the beds. Strata or beds are the single most characteristic feature. So if we go back to that, you can see that here. Okay, well, as always, thanks for watching, and in the next video we will look at the third type of rock called metamorphic rock. Have a great day.